mental health nurse practitioner, board certified, and then clinical nurse specialist, board certified. I was first certified as a clinical nurse specialist in adult acute care nursing. I was a critical care nurse for a million years, cardiac, surgical, and medical intensive care. And some health problems forced me into a more sedentary job, and so I became a psychologist, and then I didn't know my psych meds. If you were in heart failure, I was fine, but if you had depression, I didn't know where to begin, and so I went and became a psych NP as well. So that's what all those letters are for. I always beat everyone in the letter game. So what we're going to do, and I had in my old office when I could put my diplomas up, I had my wall of smartness. You know, I had everything up and, you know, all this stuff and my words. And I had one patient one day, the day I hung my PhD, I had to go to the front office. And so I come back and he's looking at my diploma like this. You know, and I thought, oh, he's kind of impressed. You know, he's got my PhD and he's looking at my diploma. And he actually goes like this. That is a really nice frame. And then he goes, look at that border. That must have cost you $400. So it teaches you never to be full of yourself, no matter what you've accomplished. It's true. So what we're going to talk about today is kind of the psychopharmacology. It's one of a series of 3 talks on the psychopharmacology of medication, which means we're talking about the S word, science, right? Which was my whole life before I became this, and they kind of merged together nicely. What I want to do is give you some background science and physiology. Am I talking too quickly? No, okay. About how neurons work and how brain physiology works. And then I want to go through a little bit of med speak, just so that when you hear, he's taking, two TID and 1 before HS. You hear these little words floating around. I want to give you a little bit of background of med speak so that you understand a little bit of that. Or when you even see prescriptions written or something like that, you can decode them. And then we're going to start through, hopefully today, SSRIs and tricyclic antidepressants. And I say tricyclics because I still use them. They're actually better drugs than SSRIs. The trouble is they have a higher side effect profile, but people don't like to use them. But sometimes I'm stuck, and I turn to them, and they're of great help. All right? Please make this an open forum. Any questions, please don't be shy about raising your hand or chiming in any way. All right? So, psychotropic meds. Sounds familiar. Yeah. The nervous system of our body is kind of divided into 3 parts, okay? We've got the nervous system, and my computer won't link up with our projector. So I'm going back to the days when professors taught with blackboards and erase boards and things like that. We've got our nervous system, which is based on neurotransmitters. What are those? Well, we know that neurons in our brain, and this is a gross simplification of what a neuron looks like, they're cells that don't connect with each other, okay? Here's the cell body where all the metabolic machinery for the cell is. Do you remember words like mitochondria and endoplasmic reticulum and all that stuff? And this machinery makes 2 things. It makes energy for the cell to run. And what do all cells run on? ACs.
ATP.
ATP, right, great, good one. So it makes ATP, right? And it makes whatever neurotransmitter that cell's supposed to make. We're talking about brain cells here. We're not talking about skeletal muscle or anything else, okay? And these neurotransmitters are actively transported down this, and you know what this is? Axon, right? Down these dendrites. And they float across the space. What's the space called? Synapse, right? There's our axon. And your cell body. And these neurotransmitters bind on the next door cell's receptors. Now this is called the presynaptic cell. Yes.
Can we swap it because I can't see what you're writing at all?
This way?
Yeah. Can you write from that angle, or should we switch
Absolutely.
it? Okay, thank you.
That's fine. Okay, this is called the presynaptic neuron because it's sending neurons to the next cell, right? And this is called the synaptic neuron because it's the cell that's receiving the neurotransmitters. Now remember, there's like 8 zillion of these on each one. You know, our brain's just filled with zillions and zillions of these. Which are dying every day through a natural process called apoptosis, and that is controlled by a substance, I love the name of this, called thanatogens, like Thanos, right, death. So we're born with a full complement and we don't get any more. Okay, so anything that dies is gone. Okay, now, so this neurotransmitter, like a key in a lock, turns on or off the cell, depending on what this cell is programmed to do. Okay, and that's the basis of neurotransmitters. Now we'll get into more when we start talking about meds. We also have the endocrine system. Am I writing big enough? Endocrine for you to get on the camera, Janice?
I can't even see it. It's not showing up with the blue, unfortunately, but
Should I try a different color?
maybe the green might work.
All right.
It's all trial and error.
Mm-hmm. Right, is the endocrine system. And this is all about hormones. Is that better?
No. We'll have to get you some better pens for next time.
All right, thank you. So we're going to get blue because I like it. All right, this is all about hormones. And our last system is our immune system, which is all about what? No. Those fight infection. How about?
Antibodies?
No, it's all about cortisol and steroids. Antibodies would be, autoimmune. You know what? You're in the right zone because antibodies come from our autoimmune system, so they do come from. But what the immune system is really controlling are cortisol and steroids. And antibodies get in there, okay? All right. So that's our first 3 things that we need to bear in mind. And what we're really going to be talking today is the nervous system. Now, you have to realize that while most psychotropic drugs are impacting the nervous system, that these systems are intertwined trees with one shared root system, such that none can exist without the other, all right? If we have an emotional trauma, which is a nervous system insult, it's going to disrupt the routine of the endocrine system, which is going to disrupt the routine of the immune system, which is going to disrupt the routine of the neurologic system, which is going to disrupt it. Do you understand? Everything affects everything. And that's why there's mind-body connection. That's why when people experience Big-Wind syndrome, they get PTSD, because their visual intake has affected their neurologic system, which has in some way affected their immune system. It all is tied together, all right? So we cannot, so let's say your immune system's suppressed. Now your glucocorticoid levels are high. Now you're exposed to infection because your immune system's not working that well. And it's all tied together, all right? So now, next concept. We have our brain. Okay? Sort of. That's our cerebellum in our brain. And we have our spinal cord, which goes down here. Okay? By the way, this cerebellum is where all of your major centers are that tell you to breathe, to eat, for your heart to beat, and things like that. Okay? And you'll notice it's at the base of your brain. Okay? So now we've got your skull. Well, it's surrounded by a membrane. And this membrane is called a meninge. I spelled it M-E-N-I-N-G-E. Okay? The goal of this meninge, and inside this meninge is cerebral spinal fluid, CSF. Why do you think our brain and our spinal cord are floating in a balloon of CSF? Yeah, so every time we walk, right, when our brain, and our spinal cord isn't knocking because it would get upset, it would get irritated. So it's always floating in this nice bath of cerebral spinal fluid, okay? By the way, itis is the word for inflammation, and if this meninge becomes inflamed because of bacteria, what disease do you have? Meningitis, right, correct, okay? Now this is surrounded by your skull. okay? And this is important to know because if you get a TBI, right, a traumatic brain injury, and your brain starts swelling, right? It can only swell so much because what's in the way? Your skull. When you get a bruise and you get swelling, your skin can swell a lot, right? But your brain gets in the way. So if your brain swells too much, where's the only place that this cerebellum, this thinking, heart rate controlling, breathing part of your brain can go? Down into your spinal cord. And that's called when the brain herniates. Have you heard that term? And once that brain herniates down in the spinal cord, you're gone. You're brain dead. My son is an oral and maxillofacial surgery resident, and they were using a trauma program. And so someone had some TBI, and they were doing surgery, and they opened up the skull, and you could see the brain, mushroom out as soon as they took the piece of skull out, because there was so much pressure in there. And as they were doing whatever they were doing, all of a sudden you could see the brain go, poof, it just settled down. And the attending surgeon said, that's it, she's gone. She's gone. Now whatever we're doing is just salvage because she just herniated down. So that's how people become brain dead. And that's why you can't get them back. Because now this part of the brain is just squished in this little space and you can't pull it back up and there's too much pressure. People stop working, okay? And now what we have are nerves that come out, okay? In all kinds of directions that control all the things that happen in your body. And at the bottom are a lot of nerves. So many, because they have to go to all your lower extremities. It's called the cauda equina, which means horse's tail in Latin. All right? My last little bit of information okay, so this meninge, okay, is the psychopharmacologist Darth Vader, because it's also called the blood-brain barrier. Have you heard that term? And that's because it's made of lipid. Lipid is fat, okay? And our challenge is to get drugs to the brain. And we can only get drugs through to the brain if they're lipophilic. Lipophilic means they're friendly to fats. What would, if they are fearful of fats and they don't like fats? Fearful of fats, what would they be? Lipophobic. Yeah, that's the medical term. Lipophobic, right? Medications that like water are hydrophilic, and if they don't like water, they're hydrophobic. Okay, so most psych meds are lipophobic. And we can't get them through the blood-brain barrier. If only we could get serotonin through the blood-brain barrier, we could give serotonin. If only we could give and fix depression easier. If only we could give dopamine and get it through the blood-brain barrier, we could fix Parkinson's disease, but we can't. We can get drugs through that make cells produce more dopamine or that keep cells from recycling serotonin, or we have to go through the back door with a lot of these meds. But it's important that you understand that physiology and why that's happening. Okay? Back to the neuron conduction. Just for the sake of interest, because I assume you're here because you're actually interested, not just because you're interested. I know many of you aren't. The way these neurons really look is more like this. So, they've got their dendrites. And they're coated with a myelin sheath. And the way impulses travel through the nerve is what's called saltatory conduction. Hopefully I'm speaking clearly enough, Janice, that people will hear. And nerve impulses don't just travel down the nerve, they skip. They go bing, 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 okay? They jump from each of these little nodes to the next. So what happens if these little nodes of myelin become hardened, sclerosed in multiple areas? What that disease might be. Multiple sclerosis. And so if you're not getting diseases transferring really nicely and smoothly, are you going to have nice, smooth, and coordinated muscle movements? No, you're going to start to have the stilted conduction that people and all the problems that people with multiple sclerosis have. what I'm trying to do is show you that medicine really does make a lot of sense. You know, when you boil it down and understand what physiology is, you can explain everything, and it's really quite interesting. Okay, all right. So now, we need to know the different components of the central nervous system. Okay? And first, this is the central nervous system, CNS -BC, board certified. I'm not, it's just a bad joke. Okay. So first we have the somatic nervous system. And that is skeletal muscle. Okay? That's all of our muscles that move outside the spinal cord, right? And the neurons work in different ways, and we don't need to talk about them. We also have the autonomic nervous system. This is all voluntary stuff, okay? It's somatic. We have the autonomic nervous system. And this is more basic operating procedures. We're not really thinking about how to process this unless we're using biofeedback of some sort. And there are two parts of the autonomic nervous system. There's the sympathetic nervous system, and that's for nervous system. What's the sympathetic nervous system? Does it keep us calm, or does it?
Is that the one for stress response?
Yes, that's stress response. This is fight or flight. So this is you walk through the woods, right? You see a bear, you know, all of a sudden your stomach drops, and your stomach drops because your body goes, I need to flee or I need to fight. Your stomach drops because it immediately shunts blood from every place where it's not needed to your heart, lungs, and brain. And that's the pit in your stomach you feel. All of a sudden your stomach's got blood that's left, and you feel it, right? All right. And I'm always telling people who are anxious, is there a bear? I use that analogy a lot. You know, there's no bear. You're feeling like there's a bear. But you have to tell yourself, am I really in that danger? You know. Now the trouble is, we've still got this back from our caveman days. Because when we were foraging for food, if we ran into a velociraptor, we had to either run or be lunch, right? So it was a really great adaptive mechanism. The trouble is the response hasn't gone away, but there are no more raptors. And it still goes into gear sometimes when it shouldn't. And so that's the panic that people feel. It's still in our body, but we use it improperly sometimes, yes.
Is that the amygdala part of the brain?
No, I don't believe so. What do you got there?
I thought I remembered that.
I don't believe so, but I'm not an expert on it, so I couldn't say. All right, and I explain that to patients so that they know it's just your brain pulling tricks on you. You know, you've got that response, and you're just responding to an inappropriate situation that may be a 2, and you're having a 10 response. So this is the sympathetic nervous system. We've got sympathetic, autonomic, sympathetic, fight or flight. This is involved with energy expenditure, right? Got to flee. And we have the parasympathetic nervous system. And the parasympathetic nervous system is involved with energy storage. And we always have to be storing energy, but there's a problem. Because back being a caveman, were we better off if we were just chill? You know, just walking through our day, right? And the problems came along, we got ourselves ramped up. Or were we better off if we were ready for action, right? And something was just keeping us down, but we were ready to go. Which would work better evolutionary-wise?
It's better to be ramped up.
Better to be ramped up, right. So the parasympathetic nervous system's job is to keep the sympathetic nervous system tamped down, okay? So it's always overriding the sympathetic nervous system so that we're ready to go at a moment's notice, okay? So this keeps the sympathetic nervous system calm, and it's involved with energy storage. Now, have you heard the term vasovagal response? Oh, they just had a vasovagal response. That means somehow someone's parasympathetic nervous system became overstimulated and tamped their sympathetic nervous system down just a little too much, so that now all of our energy use was gone and we just fainted. It's only because this got ramped up. Vasovagal, the vagus nervous system, affected our our vasculature, and just call it, I won't go into the whole thing because I don't want to waste time, but that's what's happening, okay? Now, we also have to talk about the limbic system. What's the limbic system? Anybody know?
Balance?
Not quite. That's in the cerebrum. Yeah. Nice try.
Emotions.
Yes, emotions. Perfect. We do things for only one of two reasons. Either looking for pleasure or avoiding punishment, really in the end. That's why we are motivated to do anything, if you take it down to its most basic level. And limbic system contains those reward and punishment centers. And it's kind of filtering through our entire brain in different ways. So that has an effect on what each of us perceive is going to be a threat, a reward, punishment, right? Because it's different for what all of us are. You know, I love public speaking. I like getting up and talking. The next person is afraid. Why is it? Because this is the way my limbic system is programmed. It's just different for everybody. So no response or action can be entirely objective, because the limbic system has the final say on what the structure of a response will be as it leaves the brain. Because everything's filtering through everyone's in particular limbic system. Okay? So what we're interested in are, what are the neurotransmitters in the limbic system? Because that's what we're affecting with our psychotropic drugs. Okay? So everything we're talking about is in the limbic system, the qualities of the blood brain. That's what we're talking about, okay? And there's two types, and there's two things we have to think about. One are monoamines. Mono meaning one, amine meaning amine group. You know, it's just a kind of organic structure, which nobody here, including me, cares about, right? Suffice it to say, that's what it's referring to. There's one amine group, okay? And there's one kind of monoamine called, and I'm sure you've heard this term, catecholamines. Have you all heard of this? Okay. And there's many catecholamines. One is dopamine. These are just chemical structures, all right? And dopamine can be excitatory or inhibitory, depending on the receptor, all right? So it just depends all on the receptor. Remember we talked about receptors? And I told you receptors do different things on different cells, right? So it all depends on the cell. For example, if you have too little dopamine in the substantia nigra of the brain, you have Parkinson's disease, right? So people with Parkinson's have too little dopamine in the substantia nigra. Can we just give them dopamine? Why not? Blood-brain barrier, right? So what do we give them? Levodopa, which is the precursor of dopamine. We can get that through the blood-brain barrier. So we can make the cells that will respond to levodopa make more dopamine, right? Cinnamon, that's the drug. So we can help them. And Parkinson's is a disease of volition, right? People can't get moving, right? But once they do, you see the shuffling gait, because they finally get rolling, you know, and you see the cogwheel tremor, right, and flat facies, okay? But what happens is after a while, those cells keep dying off. So we can keep giving levodopa as long as there are enough cells available to respond to the levodopa and make more dopamine. They finally aren't enough cells to respond. That's why we can't. That's why people still deteriorate. All right. Too much dopamine in the nucleus accumbens gives you schizophrenia, because dopamine makes you think. Okay. And if you've got too much dopamine in the nucleus accumbens of your brain, that area of your brain, you're going to think, which means hallucinations and delusions, right? What's one of the side effects of psychostimulants, which are giving you more dopamine? Hallucinations, right? And so, you know, now you know where it's coming from, because the drugs don't care where they go. They go everywhere. And so sometimes kids have some mild hallucinations from these drugs. Remember, any drug we give doesn't care where it goes. It goes everywhere it can get to, yes.
What happens when a schizophrenic takes a hallucinogenic drug?
So these are big problems. And more so because I'm very averse to giving a schizophrenic a psychostimulant, because that's kind of a bad combo. But what about a bipolar? You know, because a lot of bipolars have, you know, ADHD, and they really need their impulsivity tamped down. So sometimes with great care, and I always get a letter from the insurance companies when I do this, I do combine a psychostimulant with a mood stabilizer, and then I always get a letter from the drug company. You know, you realize this drug can be causing it. You have to do it with great care and start at very low doses and see where you go. I've had really good success doing that. I'm just very careful to titrate my psychostimulant up very slowly. I will not give a stimulant to a schizophrenic. That's just playing fire. Yeah, I'm just asking for trouble. Okay? All right. If you don't have enough dopamine in your frontal lobe of your cerebral cortex, what do you have? ADHD, right? So you can see it's not just a neurotransmitter, it's where is the deficit, where is the excess, you know, and that'll determine what the problem is, right? Our second catecholamine is epinephrine. And our third is norepinephrine. Anyone know what another word for epinephrine is? Adrenaline. Two words for the same thing. So we have adrenaline and noradrenaline, or epinephrine and norepinephrine. They're absolutely synonymous, all right? So these are catecholamines, and you know what they do, right? They're implicated in alertness, wakefulness. You know, it's your epinephrine that gets you going when that fight or flight system is engaged, all right? And then we've got another, catecholamines, right? Dopamine, okay. We have indolamines. Indolamines, major one is serotonin, which we're very interested in, right? That's almost what we're dealing with. And serotonin is usually inhibitory. It regulates mood, eating, sexuality, dreaming, sleep, arousal. But we need a good level of serotonin in order to have a good mood and low anxiety. Okay? So that's why I'm always interested in serotonin. All right? And then, I'm doing this wrong. Hang on. We got monoamines, catecholamines, indolamines. Right. And then we've got a whole other group of drugs called acetylcholine.